Welcome to the data science sessions here on Python Tutor. My name is Barak Daniel, and today we are going to look at data acquisition and preparation. I hope you can pay attention, get a piece of pen or paper or laptop or notebook or whatever, and let's get started with today's lecture. So today I want us to discuss about data acquisition briefly, then we shall put much of our emphasis on data acquisition systems, and we're going to focus on just a very simple system. What is data acquisition? Data acquisition is the process of collecting raw data from various sources, let's say sensors, databases, or surveys. Now, this data is then cleaned, processed to make it suitable for analysis. This process is very important in data science because it ensures that data is of high quality and can be used to generate accurate insights. Even though it's very important in data science, data acquisition isn't a very simple task. It's very challenging. As I've said, very challenging. And there are so many sources of data. Let's say there are common ones like sensors. Sensors are devices that can measure physical quantities. Let's talk of temperature. When you look at a thermometer, when you look at pressure, when you look at humidity, and these often collect data in real time. In just the previous lecture, we discussed about the different velocities of data velocity, where we had real time, near real time, batch, and so on and so forth. So for sensors, for them, they collect data in real time. Yeah, then the most popular source of data when we're doing data acquisition are databases. Databases are simply repositories of data that can be accessed and queried by computers. And this is actually the most common source of data in data science. And then earlier I discussed about surveys. You can collect survey from a population of people, and then you clean it, you do the entire process of data acquisition. So the process is simple. You need to identify data sources, collect this data, clean it, store this data, analyze it, and communicate the results. And that is quite complex and challenging, though an essential part of data science process. By acquiring high quality data, data scientists like you who's listening to this live stream can generate more accurate insights and make better decisions for their companies or wherever you are. So, that being said so well, I want us to put our main emphasis today on data acquisition systems. Why data acquisition systems? Is because we are going to look at how we can sample real world data, process it, and then display it on any output device. Let's say a very simple LCD screen. This data acquisition system that we are going to be looking on works as a microcontroller based digital thermometer for measuring temperature. And its role is very simple. We are going to look at one whereby it displays a fever just in case your temperature exceeds 37 degrees centigrade. And that is a mark of showing that you have a fever on you. How can we build such a system that will collect data in real time, process it, then output information after being cleaned and then analyzed to assure the person that is displaying it to that you either have a fever or not. This one, when we're working on this data acquisition system, what's wrong with this machine? We shall follow a very simple pie chart. No, this is a flow chart, the one that you see on your screen. So this one, at the start, it needs to start a program. When you start a program, it needs to declare certain variables now at the second phase, and then set LCD parameters and also set post for input or output. Then later on, it needs to initialize the LCD screen and display the logo and wait maybe for 60 seconds to stabilize as we work on collecting data. Then we shall initialize DS18S21, which is a microcontroller that I'll be discussing on later on in this lecture. So we proceed down here where we shall read data from this microcontroller and then convert the display. We convert whatever we've read to display into a displayable format, So when we convert it, if a result that we've received exceeds 37, let's say it's 40 or anything, we take on this route that you're seeing on your screen and then display that you have a fever alongside someone's temperature. So we go back and then they need to record some other person's temperature, or repeating the process. And there's also another option. If this person has a temperature that is 37 or below, actually below 37, that means we shall display something like you have a normal temperature and then their temperature, and then it needs to loop back into this, and there is a continuous loop between the display and then the reading of the data from this microcontroller, the DS18S21, and then converting our collected data into a displayable format. So that process of reading data is to collect the data. Two, in converting, we are trying to clean this data and then analyze it. When we analyze it down here, we try to determine, is it 37 and above for a fever to be present, or 37 and below for a fever to be a negative. That is what data acquisition is all about, and this is a system that we are going to be looking at this evening. So one of the microcontrollers that we are going to be looking on today is the PIC16F84. What does this do? This is one of the most popular microprocessors that we have in this world, and I'll give you just a very brief discussion about this microcontroller. The PIC16F84 is I think it's an 8-bit microcontroller that was introduced back in 1993 by Microchip Technology, which exists to this day. It's one of the most popular microcontrollers in the world and has been used in a variety of applications. Let's say simple devices like the one that we're going to be focusing on today, a motor, the way you can turn on a light in your home, or it's used to measure temperature, like the user case we have today in processing power or memory. It's also used in educational projects because it's inexpensive. So when we're carrying on educational experiments in the university or in the institution, it's affordable. Then it's also used in prototyping new ideas because it does not consume a lot of power. That is the PIC16F84. And what sets a microcontroller apart from other processors are special circuits to deal with the needs of real-time applications. Because since they do not consume a lot of power, there is high possibility of processing data in real time. So one of the features of the PIC, actually the entire PIC family, and other microcontrollers that are being produced by Microchip Technology, is that they follow the Harvard architecture. The second one is it improves the bandwidth over a traditional von Neumann architecture. If that sounds like Chinese to you, the von Neumann architecture is something that works on almost all our devices today. It's a very popular architecture in computing these days. and we can define it as a design for a computer that uses a single memory for both instruments and data. Actually, something that we're going to work on today will follow the same architecture. This design was first proposed back in, I think, 1945 by John von Neumann, whose name was built into the name of this architecture, and it's the most common architecture in computing today. It follows just a few components. It has the algorithmic logic unit, the ALU, if you've heard of that, the control unit, the memory, and then the input output IO. And then those are the main components of the motherboard if you've studied some computer somewhere. The von Neumann architecture works on fetching instructions from the memory. Then after fetching the instructions from the memory, it decodes them, then executes them. So when I discuss about things to do with fetching, decoding, and then execution, what comes back to the back of your mind is data acquisition, the entire process of data acquisition. Another feature of the PIC is the PIC16FXXX has a 13-bit program counter capable of addressing an 18K by 14 program memory space, which is efficient. It has a watchdog timer. It has an RISC instruction set and an SOIC package. Well, let me break down these two for you to understand them, because you're going to need these terms later on in this lecture. When they say that it has an RISC, which I often call RISC instruction set, you simply mean that this is a set of instructions that are designed for use in a reduced instruction set. Actually, RISC stands for Reduced Instruction Set Computing, and it's RISC processor. The RISC processors are designed to be simple and efficient, and they typically have a small number of instructions. So that means the processing speed is quite higher. Then when they say that one of the other features of the PIC is the SOC package, I beg your pardon. When they say one other feature is the SOC package, this one down here, let me try to mark it down so that you're not lost. This, when they say that it has an SOIC package, they are trying to say that it has, SOIC stands for Small Outline Integrated Circuit, and it's a type of integrated circuit package that is commonly used in microprocessors like the PIC itself, and they're often rectangular in shape and have 16 pins. This will make sense as we continue on. And they don't just have 16 pins, but they have 2 rows of 8 pins each. Okay, so let's look in particular at the PIC16F84 microcontroller that I've been telling you about, that is from Microchip Technology, and a most popular one. One thing that you need to look at is its pin diagram. I'll be discussing more about pin diagram when I'll be talking of the pin configuration. When you look clearly into this diagram on your screen, you see a word called PDIP, SOIC. I've discussed about SOIC, which is the Small Outline Integrated Circuit, which is a package commonly used in microprocessors. Then there is a new term that we have on the desk, which is PDIP. PDIP stands for Pin Grid Array Package, which is a type of integrated circuit package that is commonly used in microcontrollers like this very one. And it's also rectangular in shape, as you can see, and have about 28 pins if you're to count very well. and are arranged in two rows, 1, 2, as you can see on screen, of 14 pins each. I hope you can see that too. So they are often large and difficult to solder. That is just a by the way. But this is the pin diagram of the PIC CF8X. Now, if you're seeing on your screen, you see some other thing which is PIC16CR8X. It's also a microprocessor. It's also a microcontroller. I beg your pardon. That is from the microchip technology family. It's also created under the same, and it's actually it is not so far different from the PIC16F84, but the difference is that it's also 8-bit and it has a variety of features including a 14-bit timer. It has a 16 input or output pins, and it has a 1024 watts of memory. That's the PIC 16CR8X, which is not so far different from the PIC 16F8X. And in my own view, I would think it's a sequel or something. Moving on. What's wrong? And moving on, they're giving us different uh, microcontrollers that are being produced by the microchip technology, where there is PIC 16F83, whose program memory is 512 flash. It has a RAM of 36 bytes. It has a data EEPROM of 64 and a maximum frequency of 10, and so on and so forth, which we shall not be looking into details here. But I want to discuss about the Dallas DS18S21. This is also a microcontroller, like you would see the PIC that we've been discussing of, but it has a few differences here and there that I'll be discussing on this lecture. The Dallas DIS18S21, if I'm to take you back a little, is a temperature sensor that is commonly used in embedded systems actually, and that's why we're going to use it in our microcontroller. I mean our system, our data acquisition system today, and it's just in a format that it has a resolution of 0.5 degrees centigrade and a temperature range of that is between negative 55 degrees centigrade to about 125 degrees centigrade, which is a very large range. If I'm to say, it uses a one-wire protocol to communicate with the microcontroller. So that means there is nothing actually. Later on, you'll see an architecture of a device, and you'd see that one wire protocol to communicate with its microcontroller. That is the Dallas 18S21. Away from that, we are going to look at its pin configuration. What is pin configuration? I've hinted of pin configuration when I was talking of a certain diagram that we saw earlier back here. Right. Let me try to swipe. When I was looking at this, I said we shall look at the pin configuration later on, as we looked at the pin diagram of the PIC 16F8X and then the PIC 16CR8X. So when we look away from that one, the one for the Dallas is quite very simple, as you see that. And pin configuration simply means it's a way in which pins of an integrated circuit are arranged. Pin configuration of an integrated circuit is important for determining how the integrated circuit can be connected to other components. If you look back here a little, or these two microcontrollers were being linked up to RA2, RA3, and all other components, as you can see on your screen, as an integrated circuit using PDIP and SOIC for those different PICs. Whereas the Dallas DS1821 simply has 3 pins, as you can see, and these are connected to the DND, the DQ, and then the V infinity, and then the bottom view, as you can see on your screen. The Dallas DS18S21 has the direct to digital temperature sensor, just direct. Then it also has an output temperature sensor of 9-bit resolution, unlike the PIC16CR8X that we said had an 8-bit, and then the PIC SICO that I don't have time to go back to. The DS18S21 can function as a standalone thermostat with a user programmable chip points of 8-bit temperature sensor with a one-wire digital interface. So I've mentioned about it that its temperature range is between negative 55 degrees centigrade to positive 125 degrees centigrade, which I think is a very wide range, if I'm to say. Just imagine if you to read some temperature in the industry, and that temperature is, let's say, something like 100 110 degrees centigrade. Well, there is no ordinary thermometer in this analog world that you place under 110 degrees centigrade and it survives. It will start boiling itself. But its operating range is just enough for it to reach such high temperatures that are beyond the boiling temperature of water, and then into cold temperatures below 0 degrees, like negative 55 degrees centigrade. It is accurate to positive or negative 1 degree centigrade over a range of 0 degrees to positive 85 degrees centigrade, as you can see on your screen. So this is very important to know the accuracy of our data. Remember, in data acquisition, the higher the quality of data, as I told you in the previous lecture, the better is our work in data science. So the accuracy of positive or negative 1 degree centigrade over that range is very important as you're using a Dallas 18S21 to determine how accurate you could be despite the results that you have at hand. When you look at such a microprocessor, it can give you a future scope of what it could do in the future. For example, it can be programmed to work as a temperature alarm. Let's say you go into a country where, like, the world is suffering from climate change. Yes, the world is suffering from climate change. So we can program this so that we can be able to know that since we are suffering from climate change, we can generate a device that is able to know that, oh, temperatures are higher than expected. And when we know that temperatures are higher than expected, or temperatures are lower than expected because climate change is too way, this device can send an alarm even on a building when there is something burning and probably smoke sensors are not working. Then it can send an alarm. It can also be improved as a system that can be integrated with a notification service. uh, let's say when if in case you're a programmer and you're tasked to build a system, and in this system you want to build something that when temperatures are high, you receive a notification that temperatures are high. You know what? You alert such and such a team to come and work on the temperatures in the building to prevent people from suffocating, or temperatures are very low, from freezing, etc. It can also be used in networking, like When temperatures go low, where you left your baby back home, you receive a text message or an email or a WhatsApp message. So that is just improving on such a very simple program that just uses a microprocessor. In conclusion, the features of data acquisition systems that we've discussed of the PIC, the Dallas system of choice, it's just a system of choice and a system of future, having unlimited scope for development and expansion. So if you've listened to me when I was discussing about the Dallas microcontroller and then the PICs from Microchip Technology, it gives you a further way of just brainstorming outside the box of how you can develop and expand on such simple systems to build complex systems that can do quite complex stuff. Let's take an example of a system that can use the available GPT. Let's say. So you create a system that can pick temperatures when they go below 37 of the body temperature of someone, and then someone has a fever. When someone has a fever, it needs to be something like that can trigger the API of let's say OpenAI through GPT to send you a recommendation of what you can do if you have a fever of about 37. Let's say you need to see a doctor or any health expertise to discuss your temperature. You understand? You need to consider maybe taking a bath or taking some medication, this and that. When we integrate such a system, it can save the health workers of so much work, and those are the results when we communicate. The last bit of data acquisition, as I was starting, I told you, was communicating. So when we expand this, we are trying to communicate. So I want you to look at this architecture in full of this system that we've been looking at, the PIC 16824 sorry. When I was beginning this simple lecture, as I conclude, I say that we want to build a system that is able to allow input, that we can just place it on a body of a sick person, and when that person has a temperature of 37 and above, then that person has a fever. If they have 37 and below, then that person is normal. So you display, and then you tell them a recommendation. So according to the flowchart diagram that we had back here, we say that it should be able to start the program, then declare variables, set LCD parameters, set ports for input output, then initialize the LCD and display the logo, maybe wait for 60 seconds or something, then initialize this microcontroller called DS18S21 by now, which I think you understand. Then read data from the DS21 and convert it into a displayable format. Then if whatever we have as our clean data is analyzed to know whether it's about 37 or 37 itself for someone to have a fever positive, or 37 or below for such a person to have a negative. And to do that, this is the entire architecture of our system. It allows input of power. Then we have our microcontroller there with good pin configurations here to different parts of the integrated circuit, and then other components here, so you can look very well at the pin configuration of this system. Then down here is where we have the rest of the physics, but this is an integrated circuit. If you look deep down into it, when you look at it, it seems as something very, very industrial, but it's something as simple as what you see there on your screen. We have a temperature of 34 degrees centigrade, and then this simple device simply tells you, you know what, you're normal, you have no problem on you. So The data acquisition systems like this one that we've discussed about are very popular and applicable in the real world. If you want to leave this lecture to apply it in your field, then you should know that they're applicable in industrial automation, which is an obvious answer because we can use them to monitor and control industrial processes. For example, measuring temperature and pressure of a chemical reaction or measuring the control speed of a conveyor belt. The second application that we can think of is medical research. We can use data acquisition systems to collect data from medical experiments. We can also use it for environmental monitoring and so on and so forth. That's all I had for you today. So I want to appreciate you for your time. Good day.